Good morning. This video is for my Tuesday, Thursday Math 146. You all had one day fewer of the preparation for topic 5. I'm going to share it with my Monday, Wednesday as well, but I'm going to speak to you assuming you haven't seen these questions. I'm going to break this into two videos. So this is part 1, which will cover the proportion problem. So again, if you are in the Tuesday, Thursday class, you have not seen this problem. So I'll explain it from the start. It says, suppose a random sample of 120 Americans were surveyed the day before the 2016 election. Suppose 48 Americans from your sample claim that they plan to vote for Donald Trump. So sometimes I like to just, on a piece of paper, keep track of what I've seen so far. So far we've seen our sample size of 120. We've also seen that 48 out of those 120 said they plan to vote for Donald Trump. If you divide that, that ends up equaling 0.4 or 40%. And just to clean this up, that is the sample proportion. So we actually won't use that right away, but it's good to just take stock of what you've seen so far. It next goes on to say that Donald Trump won 46.1% of the popular vote. So I'm just going to add that we now also have the population proportion. Is 120 an appropriately sized sample to justify the use of the normal sampling distribution? So what this means is that when sample sizes are too small, things don't actually work out in normal distribution. So then if we open up the normal calculator and start using that to make predictions, it's not appropriate if it's not going to function in a normal way. So the way we look at this is we need to know that expect that our sample of 120 will have at least 10 successes and at least 10 failures. So if you talk to 120 people, then we know that we would expect 46.1% of them to say, I plan to vote for Donald Trump. And we only know that because we know that that was the results of the election. That calculation comes out to 55.32. So that's good. That's more than 10. The other one we have to check is the failure condition. Oops, let me just undo that. It's 1 minus p, not p minus 1. This is the complement. That's the number of failures. That also has to be more than 10. So that's going to be 120 times 1 minus 0.461. In other words, that's going to be the 53.9% that won't vote for Donald Trump, would be 64.68. Okay. So both of these numbers are greater than 10, which means our sample is sufficiently large. And we know that it was a random sample, so that's good too. You may have noticed that these two numbers add up to 120. That makes sense because if you either voted for Donald, or you either plan to vote for Donald Trump or you don't plan to vote for Donald Trump. There's no in between. You will or you won't. So this should add up to the full sample. And okay, we're good to go on that. Move now says calculate the standard error for a distribution of sample proportions where n equals 120. So this is where we use this formula, that the symbol for that, we say the standard deviation. This is if we imagined all sample proportions we ever took, if we just took one sample of 120 and then another and another and another and another, and we found the proportion that said they'd vote for Donald Trump, then we would expect it to be centered at 0.461, and we would expect the standard deviation to fall within this formula. In this case, that would be 0.461 times 1 minus 0.461 divided by 120. By the way, you should be doing these calculations along because there are opportunities for calculator errors here. This, by the way, works out to be about 0.046 or about 4.6%. If you didn't get 4.6 or 0.046, you should figure out, maybe add parentheses somewhere, figure out what you need to do to calculate that appropriately. This next part I answered beyond what was asked, but it says draw the sampling distribution centered at P, plus or minus 3 standard errors. So that would be centered at 0.461, and then adding 0.046 plus 0.046 plus 0.046 minus 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 the same number. And it shows this is our standard, this is our distribution of sample proportions. We would expect infinite sample proportions to be distributed like this. And this is getting a little ahead of myself, but notice that I marked, we already calculated our sample proportion. Remember that sample proportion was 40%. So that's right there. And you can see that that is about 1 and some change, about 1 1/3 standard deviations below the middle. So we would expect a z-score around somewhere between -1 and -2, closer to -1. Calculating the z-score of this sample gets a little bit, just to be, the z-score we've described as data minus mean divided by standard deviation. In the case of sample proportions, then the data is that one sample that we took, and the mean would be the population proportion, or the same way that all possible samples would work out to equal the population proportion. And the standard deviation is what we just calculated. So that would be the standard deviation of p-hats. And in this case, it would be 0.4 minus 0.461 divided by 0.046. It's just a coincidence that there's all those 4s and 6s. That equals about -1.33. And like I said, that makes perfect sense that 1 1/3 standard deviations below the middle, that makes perfect sense for a z-score, which is the measure of how many standard deviations from the mean a certain value is, and it would be negative if it's below the mean. So that makes perfect sense. And then it says, knowing that p equals 0.461, what's the probability the sample would turn out as low as 48/120 or lower? And that's what we see in red here. The values that would be 40% and lower, kind of saying like, hey, you know, you got this sample, was your sample bizarre? And say, no, it's actually pretty reasonable that a sample proportion like 40% would come out of a sample size 120, and if with this whole setup. So the last question says, in general, data that is more than 2 standard deviations from the mean is considered statistically surprising or unusual. Is this a sample unusual? Well, the first way to answer this would just say, no, it's not, because it's within 2 standard deviations from the mean. So that's to be expected. If you want to get more specific about it, you can go ahead and look up that z-score of -1.33, and following that down brings us to the 0.0918. And what that really is saying is there's about a 9.18% chance that you would see samples as low as that, or even lower, 40% or lower, or 1.33 standard deviations below the mean or lower. So in general, 9%, almost 10% is not particularly surprising, and usually not enough evidence to say, accuse someone of sampling bias. Okay, I'm going to stop the video and I'm going to record another one for the next question, which is about quantitative variables.